where we left off in the last video, we had a mature, massive star, a star that had started forming a core of iron. It has enormous pressure, enormous inward pressure on this core, because as we form heavier and heavier elements in the core gets denser and denser and denser, and so we keep fusing more and more elements into iron. This iron core becomes more and more massive, more and more dense. It's squeezing in on itself. And so, and it's not fusing. That is not exothermic anymore. If iron were to fuse, it would not even be an exothermic process. It would require energy. So it wouldn't be even something that could be helped to fend off this squeezing, to fend off this increasing density of the core. So we have this iron here, and it just gets more and more massive, more and more dense. And so at some mass, already a reasonably high mass, the only thing that's keeping this from just completely collapsing is, we could call it electron degeneracy pressure. So let me write this here. Electron degeneracy pressure. Degeneracy. And all this means is we have all of these iron atoms. We have all of these iron atoms, getting really, really, really close to each other. And the only thing that keeps it from collapsing at this earlier stage, the only thing that keeps it from collapsing altogether, is that they have these electrons. You have these electrons, and these are being squeezed together now. I mean, we're talking about unbelievably dense states of matter. And electron degeneracy pressure is essentially what it's saying. These electrons don't want to be in the same place at the same time. I won't go into the quantum mechanics of it, but they cannot be squeezed into each other anymore. So that, at least temporarily, holds this thing from collapsing even further. And in the case of a less massive star, in the case of a white dwarf, that's how a white dwarf actually maintains its shape, because of the electron degeneracy pressure. But as this iron core gets even more massive, more dense, and we get more and more gravitational pressure. So this is our core now. Even more gravitational pressure. Eventually, even this electron degeneracy, I guess we could call it force or pressure, this outward pressure, this thing that keeps it from collapsing, even that gives in. Even that gives in. And then we have something called electron capture. Electron capture, which is essentially the electrons get captured by protons in the nucleus. They start collapsing into the nucleuses. It's kind of the opposite of beta negative decay, where you have the electrons get captured, protons get turned into neutrons, you have neutrinos being released. But you can imagine an enormous amount of energy is also being released. So this is kind of a temporary, and then all of a sudden this collapses. This collapses even more, until all you have, and all the protons are turning into neutrons because they're capturing electrons. So then what you eventually have is this entire core is collapsing into a dense ball of neutrons. So dense neutrons. You can kind of view them as just one really, 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 really massive atom, because it's just a dense ball of neutrons. And at the same time, when this collapse happens, you have an enormous amount of energy being released in the form of neutrinos. Did I say that neutrons are being released? No. The electrons are being captured by the protons, turning into neutrons, this dense ball of neutrons right here. And in the process, neutrinos get released, these fundamental particles. We won't go into the details here, but it's an enormous amount of energy. Enormous amount of energy. And this actually is not really, really well understood of all of the dynamics here, because at the same time that this iron core is undergoing through this, at first it kind of pauses due to the electron degeneracy pressure, and then it finally gives in because it's so massive, and then it collapses into this dense ball of neutrons. But when it does it, all of this energy is removed. And it's not clear how, because it has to be a lot of energy. Because remember, this is a massive star, so you have a lot of mass in this area over here. But it's so much energy that it causes the rest of the star to explode outward. In an unbelievable, I guess, unbelievably bright or energetic explosion. And that's called a supernova. That's called a supernova. Supernova. And the reason why it's called nova, it comes from, I believe, I'm not an expert here, Latin for new. And the first time people observed a nova, they thought it was a new star because all of a sudden, something they didn't see before, all of a sudden it looks like a star appeared because maybe it wasn't bright enough for us to observe it before. But then when the nova occurred, it did become bright enough. So it comes from the idea of new. But a supernova is when you have a pretty massive star's core collapsing, and that energy is being released to explode the rest of the star out at unbelievable velocities. And just to kind of fathom the amount of energy that's being released in a supernova, it can temporarily outshine an entire galaxy. And in a galaxy, we're talking about hundreds of billions of stars. Or another way to think about it, in that very short period of time, it can release as much energy as the sun will in its entire lifetime. So these are unbelievably energetic events. And so you actually have the material that's not in the core being shot out of the star at appreciable percentages of the actual speed of light. So we're talking about things being shot out at up to 10%, 10% the speed of light. 10% the speed of light. Now that's 30,000 kilometers per second. That's almost circumnavigating the Earth every second. So this is unbelievably energetic events that we're talking about here. And so if the original star was, and these are rough estimates, people don't have kind of a hard limit here. If the original star is 9 to 20, I'd say approximately 9 to 20 times the mass of the sun, then it will supernova, and the core will turn into what's called a neutron star. This is a neutron star, which you can imagine is just this dense ball. It's this dense ball of neutrons. And just to give you a sense of it, it'll be something, about maybe 2 times the mass of the sun, give or take, 1.5 to 3 times the mass of the sun. So this is 1.5 to 3 times the mass of the sun in a volume that has a diameter of about, on the order of tens of kilometers. So it's roughly the size of a city, in a diameter of a city. So this is unbelievably dense, diameter of a city. We know how much larger the sun is relative to the Earth, and we know how much larger the Earth is relative to a city. But this is something large, more mass than the sun being squeezed into the density or into the size of a city. So unbelievably dense. Now, if the original star is even more massive, if it's more than 20 times the sun, so let me write it over here. Let me scroll up. If it's greater than 20 times the sun, then even the neutron degeneracy pressure, even the pressure, even the neutron's inability to squeeze further will give up, and it'll turn into a black hole. And that's, I can do many videos on that. And that's actually an open area of research still on exactly what's going on inside of a black hole. But then you turn to a black hole where essentially all of the mass gets condensed into an infinitely small and dense point. So something unbelievably hard to imagine. And just to give you a sense of it, so this will be more mass than even 3 times the mass of the sun. So we're talking about an incredibly high amount of mass. So let's, just to kind of visualize things, here's actually a remnant of a supernova. This is the Crab Nebula. This is right here is the Crab Nebula. Crab Nebula. And it's about 6,500 light years away. Light years. So it's still, from a galactic scale, if you think of our galaxy as being 100,000 light years in diameter, it's still not too far from us on those scales, but it's an enormous distance. The closest star to us is 4 light years away, and it would take Voyager traveling at 60,000 kilometers an hour, 80,000 years to get there. So this is a very, that's only 4 light years. Now this is 6,500 light years. But this supernova, it's believed, happened 1,000 years ago, right at the center. And so at the center here, we should have a neutron star, and this cloud, the shock wave that you see here, this is still the material traveling outward from that supernova over 1,000 years. This shock wave, or the diameter of the sphere of material, is 6 light years. So we could say this distance right here is 6 light years. So this is an enormously big shock wave cloud. And actually, we believe that our solar system started to form, it started to condense because of a shock wave created by a supernova relatively near to us. And just to answer another question that was kind of jumping up probably in the last video, and this is still not really, really well understood. We talk about how elements up to iron or maybe nickel can be formed inside of the cores of massive stars. So you can imagine when the star explodes, a lot of that material is released into the universe. And so that's why we have a lot of these materials in our own bodies. In fact, we could not exist. We could not exist if these heavier elements were not formed inside of the cores of primitive stars, stars that have supernovaed long time ago. Now, the question is, how do these heavier elements form? How do we get all of this other stuff on the periodic table? How do we get all these other heavier elements? And they're formed during the supernova itself. It's so energetic. You have all sorts of particles streaming out and streaming in, streaming out because of the force of the shock wave, streaming in because of the gravity, that you have all sorts of kind of a mishmash of elements forming. And that's actually where you have your heavier elements forming. And because, and I'll talk more about this in future videos, most of the uranium, or actually all of the uranium on Earth right now, must have been formed in some type of a supernova explosion, at least based on our current understanding. And it looks to be about 4.6 billion years old. So given that it looks to be about 4.6 billion years old based on how fast it's decayed, and I'll do a whole video on that, that's why we think that Earth was probably that our solar system was first formed from some type of supernova explosion, because that uranium would have been formed right at about the birth of our solar system. Anyway, hopefully you found that interesting. This is a fascinating picture. And if you go to Wikipedia and look up the Crab Nebula, keep clicking on the image, and eventually you'll get a zoomed in picture. And that's just kind of even more mind blowing because you can see all the intricacy in this actual photo.